Welcome, ladies and gentlemen, to another edition of Binary Life, a channel that teaches new developers how to code by solving algorithms in a very simple manner so that you can see how the thinking process takes place. And don't forget to subscribe because we're going to have multiple algorithms in the future. So today we'll solve the Collatz Conjecture Length algorithm. Let me go to train. All right, what is this algorithm about? The Collatz conjecture, I hope I'm pronouncing that very well, states that for any positive natural number, sorry, okay, so for any positive number, and this is the process. If n is positive, you divide by 2. If it's even, you divide by 2. If it's odd, you multiply by 3 and add 1. You repeat that process until you eventually arrive at n being 1. Now, for example, this is the case for 20 here. Let's try to break it down. So 20 is even. So what do? We divide by 2. And then 10 is even too, so we divide by 2, it gives 5. Now 5 is odd. What do? We multiply by 3, it gives 15. And we add 1. That's the second scenario here. And then 16 is even, so we divide by 2, and by 2, and by 2, and finally we arrive at 1. So the program will be write a program that will output the length of the Collatz conjecture for any given n. So for the case of 20, we are going to output the length of this array, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements. So this is a perfect scenario to use a while loop, because there is a series of arithmetic going on here, and we have to keep going until we arrive at 1. So we don't quite know how many cycles we will do that division and multiplication and adding of 1. When you don't know the number of cycles, it's a perfect example to use a while loop. So oops, I did not want to. Well, I can copy this so that we can have it at site here, and let's do full screen. So here I'm going to paste the algorithm. Sorry about that. What is going on? I hope I've not canceled everything. Right, this is it. So I want to place the exercise so that we can see why we're coding. Right, I think that's fine now. So this is our function. Let me just increase the size a little bit. Right. So we can say that this is an array. This is an array that stores our output as we're doing the division and multiplication. I'll just call this the Collatz array. So let's just initialize that. The Collatz array. Oops, I've switched the wrong tab. Right. So this is it. It's just an empty array. So I'll be doing this division and storing it somewhere in a temporal variable. And then let's just call that variable TMP. For now, initialize it to 0. And like I said, we'll do a while loop. Would I initialize to 0? I'll actually initialize it to n, because that's where it starts. It starts at 20 until we finally arrive 1 someday. So let me just initialize it at end. And then what is my while loop? While this temporal thing is different from 1, because we have to do that until it arrives at 1. While is different from 1, what do? What do? We're going to check if it's even, And how do we check if it's even? If we take the number and we divide by 2, and it gives us a remainder, then it means it's even. So if it's even, this is the even scenario here. So if it's even, inside TMP, I'm going to put TMP plus divide by 2. That's it. And when I divide by 2, I'm going to put it back here, and then I'm going to take for the case of 20, this is going to be 20 divided by 2, and it will be 10. So it's going to put back 10 inside TMP. So TMP is going to change in value, and then I'm going to push that new value inside our Collatz. So it's going to push 10 inside the Collatz array. It's going to push 10, meaning that we're going to lack 20. So I should probably initialize this array with the first number 10. That's it. Then when I push 10, it continually will push in the other one. So I'm going to push inside the Collatz array. I'm going to push the new TMP. So let's start again. If it's even, for the case of 20, that's the case is actually even, is going to divide by 2, and TMP is going to change from 20 to 10. That's it. 20 to 10. That's it. And then I'm going to take the new Collatz, that's the 10, and push inside this array here. Here. Is it here? Right. So let's deal with the else case. If it's odd, this is the odd scenario. We're going to, inside TMP, we're going to put TMP. It says when it's odd, we multiply by 3 and add 1. So we're going to put TMP multiply by 3. All of that, and add 1, and then we're also going to push that inside here. So this is a repetition here, so I can just cut it, because whatever the case, odd or even, is eventually pushed inside the array. So I'm going to bring it out of the for loop. So TMP will change, and when it comes out of the not for the if loop. So TMP is going to change when I finish all of the execution of the if loop. I just push it inside the Collatz array. So that's it. Right. And then at the end of the day, let's see. Let's console log our Collatz array to be sure that we have the right thing. This is it here. Oops, not that, that's a mistake. I'm going to, again, I think I made some errors. Right, let's copy this and paste inside here. And I'm also going to paste to console.log the initial number n. So I can come out of this loop here, come out of the full screen, not loop, and so that we can execute this code and see. So if I run this code, what do we have? Right, we have something like 20, and we have the right one, the right sequence. I can actually return the length of this array, because we're asked the number of Collatz sequence numbers we have, something like that. All right, so let's run again the array. I think it passes the test, and let's submit. Yes, every test is passed. I think this is quite an easy one. So let's bring it back to full screen and do some cleanup. I just wanted to have the exercise on site. So we already know this is even. This is a one-liner. When it's a one-liner, I can actually even get rid of I think I can use something called ternary operator. Is it even? Exclamation sign. I'm going to do this. Else it means it's odd. I'm going to do this, and it's the same, actually the same thing, something like this. And then I remove the console logs. We're just trying to make everything simple and clean, and writing in as few lines as possible. Let's test again to be sure that nothing is broken. I think I don't need to put the word if. I just do that. Let's test again. It passes, and let's submit. I think if I remove the parentheses, no, why don't I just leave it like that? I think that's good. It's better like that. So let's submit the code, and let's see if there are other solutions. It looks like something we did. Let's see. So he initializes L to 1. Well, I think it's the same thing. We initialize at N, but it starts at 1 because eventually the division and multiplication has to arrive at 1, so he just puts at 1 and then checks if the number is greater than 1, because we started from N, and we're going down towards 1. So far as it's greater than 1, we keep doing this and incrementing the number of times we are doing the division. I think this is more efficient than what we did, because it's the same logic, but here this L is like a counter that counts the number of times he does this arithmetic, and we stored it in an array so that we can do the length of that array. And an array consumes takes space in the memory. This one is just a variable that increments, so it takes just one space if you wish. It always has one value, so this is more efficient. Basically, this is the same algorithm like the one up, just naming beta variables instead of L. He uses counts. What's this? Well, this is recursion. If the original number is 1, we return 1, and if it's greater than 1 but it's even, we recall this function. So the recursive function, this is cost intensive for the processor, I think so, and probably even the stack memory. If you had a stack overflow, this can actually lead to start up a stack overflow for a very big number, I think so. I think for this algorithm, this is an overkill. This will be an optimal solution. This one is just a one-liner, but it's actually the same thing like the first algorithm we saw. Is that so? No, not the case. This is actually the same like this overkill, because there's a recursive function called here. Yeah, that's it. Like I said, I don't think this is optimal. I think the first solution it's better. This is somebody that it looks like he did like us, as we wrote the same algorithm like we wrote. Alright, so I'm going to stop here, and see you in another video solving another problem. And don't forget to subscribe. There will be hundreds and hundreds of algorithms coming. Have a nice day.